Hi there, everybody. Yeah, yeah. So it does lead on from the previous presentation quite a bit, and also picks up on one of John's questions as well about understanding the difference between threads and cores and logical processes and so on. So hopefully, I can address some of those questions. The reason that I came up with this presentation, this set of slides, was some work I've been doing for a customer recently, where we've got a system that's quite intensive in processing data, and even though we kept deploying onto targets with more and more cores, we wasn't seeing any as the benefit that we expected to see in the application. So we had to investigate this LabVIEW execution system quite a lot and kind of clarify my knowledge as well. So there was some gaps in my knowledge. So yeah, so let's start. So first of all, going to take a little just a little introduction, just giving a little overview. We'll have a look at who does what in the whole chain of things here, from the application down to the processors. We'll take a look at how work runs, how the low-level tasks are assigned onto threads and cores, and then how the LabVIEW execution system itself works, how that schedules work.
Still up for me. Okay.
We'll take a look as well at and then how we can customize that, how we can customize thread allocation within the execution system. And then I've put a few guidance notes at the end to try and steer people from what I've learned and the problems I've had, things that can be helpful. So just a bit about myself. So yeah, I'm David Maidman. I'm a certified LabVIEW architect, a certified professional instructor. I've got over 20 years experience developing LabVIEW applications for measurement and control. And this starts right back to my days at university, where I studied electronic systems and control engineering at Sheffield Hallam University. So the relevant point about that is, firstly, I studied electronics and control. I'm not a computer scientist. Okay, so anything that I say is wrong is not my fault. And also, just want to pick up on this date really of this year of 1998, because it's quite relevant to the start of all of this presentation really. So if we go back in time to 1998, here's me at my university, Sheffield Hallam University, and this is where I was first introduced to LabVIEW. So it was the main software tool that was used in the control systems labs. So in my first year, first practical labs, we was introduced to LabVIEW. And also in 1998, the version of LabVIEW that I was using would be LabVIEW 5. And this is where we saw the introduction of multi-threading. Okay, so this was the first version of LabVIEW that supported multi-threading. And the first thing I did as part of research for this presentation was I dug out the release notes, the upgrade notes for LabVIEW 5. And sure enough, there's confirmation. So LabVIEW 5 includes multi-threading. And just to I found this quite funny myself, but just I thought it was good to put it in the context of what things were like back in 1998. We've also got a comment here stating that LabVIEW is year 2000 compliant. So in 1998, we was all worried about the millennium bug, and you know, it was very different to the kind of computers that we take for granted now. So digging deeper into the upgrade notes, we've got another statement here on multi-threading that explains, you know, the fact that LabVIEW has multi-threading technology. that we can run different parts of our application independently, and so on, all of this nice stuff that we hope to be able to use. And they have a comment at the bottom saying, using multi-threading, you can take full advantage of computers with multiple processors. So what I've got here is I've shown a little system with an application, the operating system deploying onto two processors, two cores, as I've labeled them here. Okay. However, in 1998, desktop PCs were single processor systems. Okay, so it was rare, very rare to have multi-core systems. So at the time, the CPU that was used most commonly was an Intel Pentium 2 that had one core. Okay, so a single core processor. So if we got one core, we can view that as, and then it was one hardware thread. Okay, so from the point of view of, if we're looking in Task Manager, we'd just see one CPU. That's the way to look at it. So one hardware thread to execute on. You could get multi-processor systems where you could have multiple Pentium 2s working together, but this was in high-end workstations. So when I was at university, in the labs where we did any kind of CAD or anything like that, any kind of PCB design and stuff, we didn't do it on desktop PCs. We had special workstations. So you may have found multi-core processors there, but not in everyday desktops that we had throughout the control system labs, for example. So just a real quick kind of overview of how processors have changed since 1998. So back in 1998, as I said, we had Pentium 2, which would be a single core processor. So we got one core, one logical processor. Okay, so I explained some of these terms a bit more as we go on. And then by 2002, we're on to the Pentium 4, and that's where we introduced hyperthreading. Okay, so we have one core, so one physical core, but we can view that as two logical processors. Okay, so the OS sees two CPUs. Again, I explained some of this in a bit more detail as we come on. Then roughly around 2006, we have the Core 2 range, where you can have Core Duo, I think it was called. So you can have either 2 cores or 4 cores. So they were independent cores on separate physical modules. Okay, so multiple chips. Then as we come to more modern times, from 2008 through to now, we've been using the Core i series. I've shown just up to i7s here. And on modern CPUs, we got lots and lots of cores, and importantly, many, many logical processors. And very often these can be on one processor, on one chip, one socket. So again, I explain this a bit more as we go on. So if we take a look at my laptop, just as a little benchmark, just an average laptop, I'd say, for a developer, I've got, so here in from the resource monitor, it tells me I've got one socket. Okay, so that's one physical CPU package. So one chip is the way that we can look at it. And within that CPU, we have 10 physical cores. Okay, 10 cores within there. But it's telling me I've got 12 logical processors. Okay, so processors is as we see it from Windows. So the reason that we've got more processors than we have cores is that some of those cores will support hyperthreading. Okay, so on a core that supports hyperthreading, you have 2 execution streams. Again, don't worry about that too much at the moment. We'll come on to that later. So for my laptop, I can see 12 logical processors. And the way we can view that is 12 hardware threads that get exposed to the operating system. So within the overall system, so from our application to our processors, let's just take a quick look at who does what. So the application. So the application is where we have our business logic. Okay, so we develop our software to perform our measurement and control task, for example. And when our application runs, it makes requests on the operating system. So it gets the operating system to save disks of file, to update the user interface, to create threads as needed, and so on. So the application makes requests on the operating system. The operating system handles those requests and coordinates with the hardware. So it sends instructions to the CPU, which the CPU can then execute. So the CPU, the core, the processor, terminology to be defined later on, executes low-level machine instructions. Very simple things, okay? So it's not clever at all. All it can do is move values around, compare values, go to an address, and so on. So it just executes real low-level instructions, okay? It does it well, but it does it slowly. So if we're looking at our system overall again, the way we can look at it is our application is our intent, what we want the system to do. It defines what needs to happen, how the user interface should look, and so on, makes decisions. It sends those to the operating systems, which is the management layer. So it's going to decide of all of the work it's been passed, where that work is going to run, on what core, if there's multiple cores, or what thread, hardware thread. It's going to decide how stuff fits in with priorities and so on. Okay, and then the execution layer is just carrying out the actual instructions on the cores. Move this here, move that there, access this piece of hardware. So let's think about how things actually run. So here I've showed a system with an application that has different parts of the application that want to run independently. So multi-threading enables different parts to run independently. Okay, so whether that's concurrently or in parallel is not important at this stage. Okay, our application is structured to try and give the illusion of things running in parallel, whether it's true parallelism or not. And with multi-threading, it allows us to take advantage of computers with multiple processors. Okay, but if I go between these two, just notice from the application point of view, we're making requests on the operating system, and it's the operating system that's allocating the work to the multiple cores. Okay. So if we go back to 1998, when I had a single core, we still had the concept of threads, okay? And LabVIEW at this time, as we know, introduced multi-threading. And how did that work on a single core PC? Well, what would happen is we would make requests of the operating system for the threads for our work to run on. And then the operating system would time slice these activities and pass them to the core, to the CPU to execute, and it would switch, the operating system would switch between these tasks. So I've shown a very simple example, just showing if I've got 4 threads. So let's imagine that they are for these different processes. And then I've just shown a simple example. So for each thread, I'm going to do instruction 1 and then move to instruction 2. Now, obviously, it's much more complex than that. The operating system may perform several activities of part of thread 1 before moving on to thread 2. Okay, but that's up to the operating system to manage. And so this is just conceptual. But when we had a single core processor, things appeared to be running in parallel. So we had concurrency, but there was clever time slicing, making use of the CPU core. Then when we get to the Pentium 4, we introduce hyperthreading. So to try and give an analogy of what hyperthreading's like, it's like one person with two hands. Okay, so if I'm doing some work, if I'm in the kitchen, I've got two hands. Sometimes I can use both hands at the same time. So I can stir a pan and chop vegetables at the same time. So I can use both my hands independently, so long as both hands don't need to use the same tool. And so long as my brain, the operating system, can coordinate those two activities. Okay, as long as I can do that, I'm able to carry out two activities at a time. So when we think about that in terms of processors, if we've got a core that supports hyperthreading, it's one physical core that has two threads, two hardware threads. Okay, and what that does is it allows the CPU to carry out two instruction streams. And this may be because if, for example, one stream is accessing memory, a memory resource, that may take several clock cycles to be able to do. So whilst that's busy, the second thread may be able to be doing useful work as well. So you don't get twice the performance. So you don't get the performance as if you had two processors, but you get an overall better throughput. Okay. So the way that might look is we have our application with our 4 areas that we're trying to run. We request that to the operating system. So this is never changing, this part here. But what we've got now is the operating system is it's still interacting with one core, but it's using two hardware threads within that core. And this is where we start to talk about logical processors. So although there's one physical core, the operating system actually sees two useful things, two execution lanes that it can put commands onto, instructions onto to be executed. Okay, so here I've tried to show some color coding between my threads. So I've still got my 4 threads, and there's some element of time slicing on each of the threads, but one thread is reserved for these two. Hardware thread is reserved for these two software threads instructions, and this other hardware thread is being reserved for these two software thread in like the set of instructions. So yeah, so when we've got hyperthreading, the single core will be seen as two logical processors. So two processors effectively that the operating system can access. If we go to true multi-core, we have two physical cores, each able to execute the instructions. Okay, so again, where I've got the color coding, that shows the switching, the time slicing of the software threads, which are being executed on these two separate hardware threads. So these are these cores. Each core has one hardware lane in this example, so one hardware thread. Okay, if these were hyper-threaded cores, we'd actually be able to have 2 lanes on each, so we'd be able to see 4 logical processors. So how does that all relate to in LabVIEW and how LabVIEW manages threads and understanding our LabVIEW execution system? So LabVIEW has an execution system. You will have seen it in the VI properties lots of times and maybe not given it a lot of thought. But LabVIEW has it uses this as a scheduling system, and it uses a pool of operating system threads. Okay. Operating system threads are software level threads, and the operating system is basically the operating system thread is a scheduled unit of work created by software. So Windows schedules OS threads and it puts them onto the available hardware as it sees fit. Okay. We can make requests and ask to use the specific CPU, but at the end of the day, the operating system will decide how the software threads are going to be distributed on the hardware threads, the hardware targets. And then our logical processor, so now I'll try to refer to it as logical processor, is basically a hardware thread, a lane of hardware execution instructions that we can execute. So that could be a single core that's hyper-threaded. That would be 2 logical processors, or it could be a system like mine where I've got 12 logical processors, which are on 10 physical cores. So how many threads does LabVIEW actually request from the operating system? So as a rule of thumb, we request 1 user interface thread, which we'll discuss shortly. LabVIEW has some internal timer threads that it uses. It creates a number of execution threads, which we should view as the main worker pool. This is what's going to do most of our work. And then it creates some additional threads dynamically for other technologies like ActiveX and stuff like that. Okay, so what I'm going to do is I'm going to cut that list down, because from that list, there's 2 areas where really we have some influence, the areas that we can use when we're structuring our application. So we have our 1 user interface thread, and then we have a number of execution threads. So the UI thread, all applications have exactly 1 UI thread. So anytime you're doing any user interface work, it's going through that UI thread, and there's only 1. It handles all the front panel updates and user inputs. So anytime you update an indicator, it will use the UI thread. Anytime you read from a control, it will use the UI thread. Okay. So also some property nodes. Property nodes influence the user interface. So some property nodes will make use of the UI thread, and also some thread unsafe calls. So for example, if a DLL is thread unsafe, it should be set to run in the user interface thread. Okay, and that's because of it's contained within that thread. It can't be influenced by anything else, and so it needs to reside there. The UI thread also also services something called the root loop. Okay, so I'm not going to go into the root loop too much here, but there are some operations. So when you do some operating system level calls or something from LabVIEW, or somehow when you manage some property nodes, or some opening some references, for example, these activities require the root loop. And the thing is about the root loop is often it requires the user interface thread to be idle. So the user interface thread, when it's idle, will then switch to service in the root loop. It has to complete that operation before switching back. So you just need to be aware of that if you have any unexpected behaviors in your user interfaces. Lags and unresponsiveness could be caused by that, or areas of code that get blocked because user interface is busy and your area of code is waiting for the user interface to be idle so that it can perform its root loop activities. Because there's only 1 UI thread, the work has to be scheduled and take turns, and this works on a cooperative behavior. So if we go to the LabVIEW execution systems, we'll take a look at what this looks like in a minute. But LabVIEW presents us 5 execution systems, putting the user interface to one side. Okay, so we have standard, which is the default execution system that's used for most application code. If you don't define the execution system for a VI, it will use the caller. And if you've not defined any execution systems, the default when you run your the main entry point is going to be the standard execution system. So you could find yourself where the majority of your code is running in this execution system. We've then got some others. So we've got instrument IO. Okay, so this I've put here suggested for a reason we'll come back to, but this is suggested for instrument communication. So, for example, visa and serial type tasks. Similarly, we've got data acquisition, which is suggested for data acquisition, signal acquisition type tasks. Okay, then we have other one and other two. Now, these are spare pools that can be viewed as custom partitions that you can use. Okay, now I said that these are suggested. That's because these names are for organizational guidance. Okay, so it doesn't imply any performance benefit. So putting IO tasks in the instrument IO execution system won't make it work more efficiently than keeping it in the standard execution system. But the thing to take from this is these are areas where we can put related tasks that we want to operate within the same thread pool. Okay, so these are the execution systems. Each execution system has system priorities. So if you take a look at VI properties and look at the priorities available, you'll see background priority, normal priority, above normal, high priority, time critical, and subroutine. Okay, so what we're going to concentrate on at the moment is these four here: normal, above normal, high priority, and time critical. Quite confusingly, in the LabVIEW documentation, when you read up on this, these four execution systems, these four priorities are referred to as normal priorities. Okay, so normal priority is a normal priority, and above normal priority is a normal priority. Okay, so that's quite confusing. They are distinct. These are just the ones that are called. They're just referred to as normal priorities. We see why when we progress a little further. So LabVIEW allocates execution threads, and if we're thinking about how many threads we're going to create, we can use this little guidance here. So we've got execution threads equals number of execution systems times the number of normal priorities times the number of logical processes. Okay, so we know we've got 5 execution systems and we've got 4 normal priorities, and then we can multiply that by the number of logical processes. So what we end out with for usable threads that we can assign our work to, we have 1 UI thread, and then we have 20 P execution threads. So usable threads is 1 plus 20 P. So if we've got a single processor, we end up with 21 threads. If we have a 16 core system, we end up with 321 threads. Okay, this is by default. This is the default. So I mentioned about normal priorities. So there's 2 other priorities. We've got subroutine priorities and background priorities. So for subroutines are a special case that doesn't behave like the other priority levels. That's because subroutines are always called within the calling thread. So if the calling sub-VI is in standard, a thread for standard normal priority, there'll be no context switch. Okay, it will stay exactly where it is and it will execute your subroutine. The other important thing to understand there is that's a bonus. That's the most efficient thing to do, to stay exactly in the thread you are and then start executing the subroutine. The thing to understand is the subroutine will not release the thread until it's finished doing the task it's doing. So it's good for short calculations that you want to perform really quickly. Okay, so you don't want anything that's going to take a long time because it will prevent other tasks from using that hardware thread. Okay, or using that operating system thread. Sorry. So it's blocking when it starts to. Yeah, sorry, I just saw a comment about inlining, but yeah, I'll pick up on that later. Yeah, so it will execute there and then inside that same thread. Background priorities don't normally have their own thread. Instead, they will use the thread of the next highest priority. Okay, so and that will be scheduled as and when within that thread. So they're lower priority. So in our VI properties, if we go to execution, this is where we define our priority and preferred execution system. So by default, the priority will be set to normal and the execution system will be same as caller. So whenever you call, if the calling VI is in the instrument IO, the sub VI, when it's called, will be in the instrument IO execution. The priority that's used will be normal priority in this case, unless the calling VI is of higher priority, and then it will be elevated. So if we think about the default settings and what this all means in practice, if the default execution system is standard and we don't change it and we don't, we stay where we are and the sub VIs are all same as caller, that means that all of our code is going to operate within that standard execution system. So that means we'll be using far fewer threads than theoretically we could be, which is why sometimes when you scale your system up, you're not necessarily seeing a big increase in performance. Okay. So when the compiler is working, it's looking for opportunities to be able to parallelize your code. So in this instance here, these 4 VIs can run in parallel. Okay. If these are all set to normal priority and all set to standard execution system, and my calling VI main is standard execution system, that's okay in this instance. So on my machine, I know that I've got 12 logical processors. So we know that these are all going to be able to sit and they'll be able to run in separate threads, even though they've got the same priority and same execution system. Also, this is an opportunity to where we can parallelize. So LabVIEW's able to kind of split these things out into parallel and use a number of threads there. Sometimes, though, we can exceed the number of threads that are available in our worker pool. So LabVIEW will still parallelize tasks where it sees it can. But what it will do is it will use cooperative multitasking to schedule the work and to then, based on the priority queues, to put that work onto the available threads. Okay. So sometimes we may want to customize the thread allocation. So if we remember our execution systems, we've got standard, instrument IO, data acquisition, other one, and other two. Okay, and we've got priorities within those. Now, it may be that we've got big chunks of this that isn't being used, and we may want to assign more threads, for example, to standard. So LabVIEW lets us do that. It lets us customize the thread allocation. Okay. So we don't necessarily want to do this by default. The times where we may want to do this is where we can see that we've got a bottleneck in our processing, or where system requirements want us to have deliberate partitioning of some of this work for various reasons. So this is easily done by updating our application ini file. So when we're in the development environment, that's the labview.ini file. When we build an application, it would be in the application ini file that sits alongside. Okay, so what we need to do is within that file have a section called LabVIEW, and then we need to add the following key. Okay, so we've got ESYS for execution system, and then we've got standards of I don't know exactly how what this works out, but what it means is the number of threads to apply to each of the thread scheme to use, basically. So if we say n equals 0, that means turn off multi-threading. Okay, so on machines we've got now, I'm not sure why we would, but you can turn off multi-threading. If you set it to 1, that's the default, means multi-threading's on. Now, I'm going to say this with some confidence, but this stuff isn't very well documented. So, yeah, forgive me if anyone knows otherwise. But if you put a value between 2 and 8, it defines a higher number of threads to create on startup. So if your processor allows you to have more, you can specify a higher starting value for each of those worker pools. The one that I've had a lot more of a play around with is this when n equals -1, and that basically tells LabVIEW I am going to give you some custom settings to use. So let's have a look at how that works. So if we define in the ini file the value of -1 to say we're going to have custom settings, we then can we can tell LabVIEW what we want for each of those pools, basically, how many threads we want to apply. And we've got a little naming convention here. So if we have ESYS.execution system .priority equals, and then we have number of threads we want to apply to that pool. So for the execution system, if we supply an empty string, that means standard. .instrument is for the instrument IO, .dac is for data acquisition, and so on. So we need to then assign tell it the priority that this we want to set the thread pool for. So normal is for normal priority. High is for above normal priority. V high is for high priority, and T criticals for time critical priority. So just some examples. If we put ESYS stdn parallel equals -1, we're saying use custom thread allocation. ESYS.normal equals 16 means we'll have 16 threads for standard execution system normal priority. Skim down a couple more. If we have ESYS.other1.high equals 0, we're specifying 0 threads for other one execution system above normal priority. If we don't define an execution system, LabVIEW will just use the default. Okay, so you don't have to define every pool You don't have to define those all in the file, just the ones that you want to customize. Okay, so just some general guidance. I've picked up a few practical tips. So if you're going to segregate this stuff, pick the right execution system for each subsystem during your architecture design. So if you remember, you don't have to change the you don't have to change the execution system for all the lower level VIs. If it's defined at the top level loop VI for that process, that will be applied. So if you know the top level modules, top level loops, whatever you want to call them, tasks, processes that you're going to design, you can assign those to a execution system. Reserve the UI thread for UI work. And there's only a few things that you may put in there. So, for example, as we said, thread unsafe DLL calls and so on all need to be done within the UI. What I would say as well is, so I've maybe not caught this here, if you've got some code in a loop that's executing and it's using the standard execution system, for example, when it calls the sub VI, and then you write the value to an indicator, that's going to cause a context switch to the UI thread to be able to update that piece of UI. And then if you've got that, let's say that's operated in some kind of sequence or case structure, and then you go to the next VI, you then have to context switch back. Okay, and if that's then going to update an indicator, you're then constantly switching. So what you can do is have a loop which is doing your work, and then just send the results to another loop to update the display. And then you know that you're not unnecessarily switching back and forward between the UI and the thread that you're allocated to work in. So although we can go into that ini file and we can allocate lots and lots of threads, don't over allocate it unnecessarily. Or don't over allocate without thinking about it. You may be causing unnecessary context switching, and there's an overhead to that. Okay, so sometimes you may have fewer threads, and you may put a specific piece of work and only that work to execute in just one thread, say, and you may get better performance from that. Where we do want to use multiple threads is where we can genuinely parallelize the work, but don't be afraid to experiment with some post-tuning optimization. If you've assigned the work, the top level items, to the worker areas where you want them to be, you can then tune through the ini file. Although you can have higher priority, the guidance is to limit things that go above normal priority to risk to reduce the risk of starvation of the user interface. So if you've got something in a high priority and it's not giving up time, and it's not giving up time to lower priority threads, you may be not executing your user interface, so your system may become sluggish. If you keep lower level VIs to same as caller, wherever possible, you're not going to have any unexpected or unwanted execution system context switches. Okay, so you can just stay where you are. Yeah, someone mentioned inlining, which is a good thing to do where possible. Sometimes we can't inline a VI, but if we can, that's I guess from that you get the performance improvement of a subroutine because you don't have to call the sub VI, and you get the benefit that it's not going to block the thread while it's executing. Just one thing, if you're working with inlining, it effectively does a cut and paste of the code in the block diagram. And if you've got quite a few levels of inlining, your top level VI can become, that's calling those, can become quite big. But yeah, definitely inlining is a smart move. Any questions?
David. So yeah, if everyone can just like show their appreciation or whatever in the with the reacting as they wish in Teams. So there is one question I've seen in the chat from Matt, and he asks, are the ini tokens that you described, are they the same ones that are set by the thread configure VI?
Yes, they are. Yep. So with the thread configure VI, I can try and show where to find that. The thing is that seemed to limit the numbers that you could apply, because it was developed a long time ago, obviously. What I might do is in the next presentation, I'll find a link to where that sub VI is. It's somewhere in the VI lib toolkit on file somewhere in that library, and yeah, I'll put a link to it if anyone wants to have a tinker with that. But yeah, they are exactly the same. Yeah.
Great, thank you very much. I think that probably answers Matt's question. Does anyone else have a question? If they'd like to raise their hand and ask it on mic, or drop a question in the chat. No, just some messages of appreciation, which is nice. Great. Well, if and thank you, David. Your talk did indeed help clear up some of the things I always get muddled over, logical cores and yeah, threads and all that stuff. So that was appreciated.
Someone's just posted a link.
Matt shared the link.
Someone's just shared the link. Yeah.
Thanks, Matt. And I
so
believe
I used that to be able to work out the ini file, what the ini file sections, because of it's not very well documented, some of this stuff. So. And some of the documentation is from is behind the hardware. Let's say it's behind where hardware is up to now. So there was a lot of digging around. Yeah.